1 second.
Dr. Russell, are you on mute?
I am muted. Sorry. So let me go back. I was saying that thank you for catching me on that too. Uh, that we're going to determine empirical formulas, but under that umbrella, we're going to be looking at percent composition. We're going to be looking at empirical formulas, which we'll see, which I'm going to abbreviate as EF, and then molecular formulas, which we can determine from the empirical formulas. All right, so we can take any molecule and derive like the molecular formula and the empirical formula if it's unknown. But the way we derive it is based on we need some information. We can't just derive it out of the blue. So a lot of times we derive the empirical and molecular formulas from percent composition data. Right. And normally the percent composition is simply the percent by mass of each element in a compound. All right, so we can find that out. There are actually very sensitive instruments that allow you to find out exactly how much of each element is present. I talked about it earlier, and I said that it was a high res mass spec, but we also do what's called elemental analysis. Right, that's done in a mass spectrometer where you have an instrument where you can inject a sample into it, even if you don't know what it is, and you can do an elemental analysis to figure out how much of each atom is present by mass, right? So we can figure out the percent composition. And the most basic way to do that is to be given a sample um, and given the mass of each element in that sample, and then figuring it out that way. So we're going to approach this a couple of ways. So the first way is just looking at determining, so this will be method A, percent composition. By mass in the sample. So let's say we have a 12.04 gram sample, and it's composed of 7.34 grams of carbon, 1.85 grams of hydrogen, and then 2.85 grams of nitrogen, right? All this really is a part, it's like a fraction, sort of a part over whole times 100, right? That's how we determine the percent composition, part over whole times 100. So the whole is right here, 12.04 grams. And then these are the parts, right? Different masses that add up to 12.04 grams. So we want to find out the carbon percentage in that sample. All we do is take the carbon mass that we're given, 7.34 grams divided by 12.04 grams times 100, right? We do that and we see we'll get 61% carbon. And then if we do the hydrogen, same thing, is 1.85 grams divided by the total, which is 12.04, part over whole, times 100. Right, and that's 15%. And by default, the last element has to be 24% because the total has to be 100. Everything has to add up to 100%. So nitrogen would be 2.85 divided by 12, and this is in grams. Right, so the total has to be 100%. All right, so that's the basic fundamental calculation for percent composition. If you're given the masses and you have the total mass of a sample, you can figure out how much of each element is present in that, within that given mass of a sample. All right, so now let's take a look at another way to approach this. Let me move this. All right, so method B would be to take the molecular formula right, and figure out based on the molecular formula what the percentages are. Let me not say that. So we can derive the percentages from the molecular formula. What we need in this case is we need the molecular weight, right? We're definitely going to need that, which is the whole, right? Always need the whole. And then we're also going to need the molecular weights of each atom within the compound. So that's going to be the part. Still the same idea. Part over whole times 100. So for carbon, let's say, I got to give you the example first. So let's look at a sample of aspirin. This is the structure of aspirin. I'm going to go ahead and put all the hydrogens in so you can see that. C O H O. And then these are all hydrogens. That's H, 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 and H. All right. So the formula for aspirin is C9, and you don't have to worry about drawing out the structure. I'm just doing that so I can show you all the atoms. H8, O4. All right. So we have, let's count it up. Hydrogens, 1, 2, 3, 4, 5, and then 3 here. That's a total of 8 hydrogens. And then for oxygen, we have 4 oxygens. So you can see that matches up. And then for carbon, every vertex in this molecule is a carbon. So here, 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 that's 6, right? You have a carbon here, that's 7, a carbon here, that's 8, and then 1 here, so that's 9. So we have C9H8, O4. So in order to calculate the molecular weight for this compound, what do we need to do? How do we calculate formula weight or molecular weight the other day when we first started talking about this on Monday? What do we do? So it's the sum of all your atoms, right? So when you do that, the molecular weight for aspirin is 180.16 grams per mole. If you take 9 carbons, 8 oxygens, and 8 hydrogens and 4 oxygens and add them all together with their atomic masses, you're going to get 180.16 grams per mole. All right. So how do we use these numbers and all this information to get the percentages of the percent composition, right? And again, it's part over whole. So the part will be for each one of these carbon. Let's say carbon first. That's going to be 9 times 12.01 grams per mole divided by the total, which is 180.16 grams per mole, right? Part over whole. Part in the top, whole in the bottom, times 100. Right? And then for hydrogen, we're going to do the same thing. 8 times 1.008 grams per mole divided by 180.16 grams per mole. And then for instance, hydrogen. And then for oxygen, we'll do the same thing. Well, it can be 4 times 16 grams per mole divided by 180. Right, and this all of these will be times 100 to give us a percentage. So if we do, let's see if I can shrink that a little bit so I can have make room for the actual percentages. All right. So let's see if we can do these calculations real quick. So for carbon, that's going to be 108.09 divided by 180.16. So let's do that, and then times 100. That means that this sample is made up of 60% carbon. Same thing with the hydrogen. You see what that number is, 8.064 divided by the whole times 100, and that gives me 4.5% hydrogen. And then with the oxygen, it's going to be 64 divided by 180.16, right? And that is 35.5%. Any questions about this part so far? Right, so we can take the masses of a given sample mass, if we know the masses, or we can calculate the masses. Either way, well, sometimes you might see an example where you have to find the mass. Or if we have a total molecular weight and a molecular formula, we can figure out what the percent composition is of that as well. All right. So those are two methods that we can use to figure out percent composition. Let's do another example, and let's do iron oxide, iron 3 oxide. Sorry about that. Right. So what's the first thing we need to do if we want to find out the percent composition?
It's the part over the whole times 100, right?
Mhm. So what do we, okay, so do we have either right now?
No, sir.
We do not. So what do we need to do? We need to find the whole. And then once we find the whole, we have a formula, right? That'll help us to figure out the part. Does that make sense?
Yes, a little bit. I think if you work it out, maybe I'll understand it better.
Oh yeah. Oh yeah. It's gonna click. So let's find the whole first, right? Because in finding the whole, we're also going to know what the part is as well. Uh, so we take iron, right? We need to know what the atomic mass of iron is from the periodic table. Can somebody tell me what that is real quick?
What we looking at?
For iron, the atomic mass for iron. So it's 55.845, but we have two irons. So we're gonna multiply that by 2, right? What do we get from that? 55.845 times 2.
111.69.
All right, cool. So that's that. That's the part. What about oxygen? So this is 16 grams per mole times 3. Right, so that's going to be 48 grams per mole. That's the other part. When we sum those two up, we get the whole. Is that right? Add the two parts together to get the whole. That's how we calculate molecular weight for a compound. So the whole is going to be 159.69 grams per mole. Right? Now we can go back and figure out the percent composition. If we take the part, so this is for iron, right? The grams per moles are going to cancel. What do we get from that? What? And then hold up, times 100.
I got 69.942.
Okay, so 69, let's say 69.9%. We'll take that. All right, so that's the, again, you can see right here, this is the part over the whole. We're just working with different values. Instead of working with masses, right? We're working with the molecular weights, but we're gonna arrive at the same conclusion. All right. There's some percentage of this compound that is iron. There's some percentage of it that's oxygen. But put together, they should both equal up to the total. All right. What about for oxygen? Let's do that. the part we just figured out over here is 48. And then we are also calculated the whole, which is 159.69 grams per mole. We're gonna multiply that times 100 to get the percentage of that. What do we get? Anybody?
I got 30.1%.
30.1%. So the total is always going to be 100%, right? We can't have anything over 100. So the total has to, no matter, even if you have 100 parts, they all have to add up to 100%. Even if some of them are fractional, even if some are less than one, whatever, they have to, everything has to add up to 1%. I'm sorry, 100%. All right, is that clear? So we didn't have either, but once we found the parts, we were able to also find the whole and then go back and use each one to determine the percent composition using the molecular formula. All right, question, any questions about that? So we can find we can find percent composition using either masses, or we can use a molecular formula to find the percent composition. All right, we don't necessarily need the masses in this case. If we have the molar masses or the atomic masses of each atom, we can use that information to derive the percent composition of a given compound. All right. All right, let's keep pushing. If there are no questions, we're gonna move on to another topic, and the topic is dealing with empirical formulas. So let me get this out of the way again. Eventually, we're gonna use this chart, but it's just not time yet. So I don't want to delete it and then have to come back looking for it. All right, so this is a subsection of molecular weights and percent composition. And so now we're going to use the information that we know to talk about determining empirical formulas. Who can somebody tell me what the empirical formula was when we talked about it in the last chapter? What the definition is? Anybody remember? Remember we said it was the reduced. It was the reduced form of the molecular formula. So it's really like a relative number of so we're going to call it a relative composition, right? Because it's not the exact number of atoms that's in that molecule. It's just a relative number of the atoms that are present. All right. And really the empirical formula, what we're looking for, what we're going to be looking for in these problems is quite simply the mole to mole ratio. We're going to look for the mole to mole ratio of the atoms that make up the compound. All right. So how do we get, if we're looking for the mole to mole ratio, right? How do we get moles? Like what's our strategy for determining like moles or calculating moles? What can we use? Even if we don't have any information whatsoever, like what relationship can we use to determine the number of moles of a given mass of a compound or a compound with a specific molar mass? What can we use? All right, can we use this? And use that relationship between grams and molar mass to find moles. So we take, if we're solving for moles, then grams over, right? So if we're given any of these values, we can figure out, if we're given any two of the values, we can figure out the third one. So in this case, if we're looking for moles, we can take the grams and the molar mass and find the moles, right? And that's what we're going to be doing when we're trying to find this empirical formula. So the first example, let's look at that. All right, so let's look at a empirical formula calculation. And we have a sample that contains carbon and hydrogen. Right, and the carbon that's present is present in 1.71 grams. And hydrogen is 0.287 grams of hydrogen. All right, so if we have those numbers, the masses of each of the elements, we can figure out the moles. How do we figure out the moles using the masses, right? If we're doing, if we're using this relationship right here, right? It's the mass over what? Right? It's going to be the, say again.
Molar mass.
Yeah, the molar mass. So in this case, we have grams of carbon and then grams of hydrogen. So the way that we're going to attack this is we're going to find out what the number of moles of each one is. So we have 1.71 grams of carbon. We're going to divide that by carbon's molar mass or atomic mass, which is 12.01 grams per mole, right? And then we're also going to do the same thing with hydrogen, 0.287 grams of hydrogen divided by 1.008 grams per mole, right? So that's going to give me two numbers, right? What number is, what does this give me? 1.71 divided by 12.01. And somebody else give me this calculation here. Anybody got it yet?
Do we multiply this by 100 as well, or
No,
just
we're
this?
not calculating percentages. We're calculating the moles.
Okay, I
Mhm.
got a 0.284 for
This
moles
one.
of hydrogen.
All right, let me get in here. Keep my units. The units are very important. Yeah, when we're doing the empirical, the only time we're going to be multiplying by 100 is if we're doing percent composition. All right, but here we don't have to do that. We're trying to actually find the number of moles of each one of these. So that's grams over molar mass, right? So what about the 1.71? What about the carbon?
0.142.
So 0.142 moles. So you can find out, like when we're doing the empirical formula calculation, if you have the mass of each of the elements, you can figure out how many moles of each element is present. So what we can say is that this is the way to calculate this will be the given mass divided by the atomic mass. Right, and this is in grams per mole, and this is in moles. Oh, I'm sorry, grams, my bad. So grams over grams per mole is going to give you moles. Right? So once we find the number of moles, there's another step to this calculation. Because what we're trying to do is we're trying to find, again, the mole ratio We're looking for the mole to mole ratio of the elements. All right, so the next step is to actually put in these numbers that we just found. So we're going to write the formula with the mole calculations that we just did. So let's do that. So we're going to write C right here, and the number of moles for carbon, we just showed that up here, 1.42. So we're going to, I'm sorry, 0.142. So we're going to put that number in, 0.142. And then H was 0.284. Now, how many of you have ever seen a chemical formula, a molecular formula written with decimals? Anybody? Right. It's always, if you think back to the law of multiple proportions, when it talks about compounds forming from certain atoms, they always form in small whole number ratios. So these are not whole numbers. So let's do this. Let's take each one of these numbers and we're going to divide by the smallest number of moles. So I'm going to change the color on that. Right, that's going to cancel, and then we're going to divide this by 0.142. So what did we get? CH what?
2.
CH2. So this is my empirical formula. So this is the empirical formula given for the amount given and the atoms given. So CH and these two amounts, this is the empirical formula. This is not the molecular formula. Right? The molecular formula gives you all the atoms with all their subscripts, so you'll know exactly how many. It's more precise, right? The empirical formula is just relative. It's the relative amounts of the atoms present. It's not the same as the molecular formula, even though you can calculate the molecular formula from the empirical formula, which we're going to do later. So these are relative amounts. Right, so these are not exact amounts, these are relative amounts. You get the exact amounts from the molecular formula. All right, so again, let's go back through this real quick. So we had the masses, we used the masses to find the moles, and then we plugged in the moles into our formula and then divided by the smallest number of moles. I didn't write that down, but I'm gonna write it here. So we're going to divide by the smallest number. Right? So we divided both by 0.142. We ended up with the empirical formula CH2. And again, keep in mind the empirical formula is a reduced form of the molecular formula. So it's not the exact number of atoms, it's a relative number of atoms. All right, so we're going to do, in the time we have left, we're going to do one more. We're going to do one more example. Let's see. I think I can squeeze it in there. All right, any questions about that first example? All right, a lot of this stuff, again, we even had this discussion this morning. A lot of it is kind of redundant because this, going through this is kind of similar to what brings back, you know, memories of doing the law of multiple proportions, where we had to find these small whole number ratios and figure out what the ratio of the atoms was and all of that stuff. And if you notice, we always we divide by that smallest number, because if you remember from multiple proportions, we had to get a fixed mass of one element and then determine how the second element combined with it in small whole number ratios. So a lot of this stuff is it's all connected. Like that's the beauty of learning science, is when you start learning how things are connected. All right, so let's look at another example. We have another example that we're going to work through. And then this is empirical formula calculation. Sorry. All right, so let's look at another example. We have a sample that has 5.31 grams of chlorine. And also it has 8.40 grams of oxygen. Right, so these are my given masses, just like we talked about up top. Right, these are my given masses. All right, and we need to find out what the empirical formula is. So let me put that question here. So what is the empirical formula? We have the given masses. What do we need now? What if we have the masses, what do we need in order to determine what the empirical formula is?
Is it the total mass of them together, of the entire equation?
Yeah, so we need the number of moles, right? So in this particular case, when we're determining the empirical formula, what we're looking for is the mole ratio between chlorine and oxygen. And so we can determine the moles using the molar mass of each element. So we're going to find out that if we take chlorine, we'll take 5.31 grams divided, and this is chlorine, divided by chlorine's molar mass or molecular weight, which is 35.5 grams per mole. And this is just based on its atomic mass from the periodic table. All right. And then for oxygen, we're going to take the 8.4 divided by 16 grams per mole. And somebody give me those numbers real quick. So 5.31 divided by 35.45, and then 8.40 divided by 16.
I got 0.149, 0.15 for
Okay.
the top one.
Okay. So let's go ahead. Yeah, let's go ahead and round that up. So 0.15 moles for chlorine. And then what about oxygen?
0.525.
Okay, 0.525 for oxygen. All right. So now we are 2/3 of the way done. We've calculated, we've taken the masses, we've used the masses to calculate the number of moles of each atom. Now we need to put it into the formula. So we're going to say chlorine. We're going to use that same number, 0.15, and then oxygen, 0.525. What's the next step now?
Isn't this when we divide by the smaller mole?
Right. So these are not whole numbers. So we want to go in and take the lowest number of moles and divide both by that. So this is going to be divided by 0.15. This is going to be divided by 0.15. That's going to cancel. So we're going to be left with Cl. And then, oh, and let me say this too. It's understood here that that's a 1. Everybody okay with that? Like we
Yes,
don't
sir.
have to show it. If it's 1, we don't have to show it. And then O, what do you get for oxygen?
I got 3.5. I was gonna ask if you're supposed to round that up or down.
No, it's fine. Don't round it. Let's leave it because we're gonna do something else with it. If we round it, then it's gonna be, we're gonna get an inaccurate depiction of this molecule. All right. So anytime, so when you're here, right, this is not a whole number. So you have to make it whole. If you remember when we were doing multiple proportions and we had some fractional number in our ratio, we just took the ratio and multiplied it by some number to make it a whole number, right? So we're going to take this whole thing and multiply each atom by 2. So this is going to, so we're going to multiply this by 2 and the chlorine by 2. That's the procedure. So when you're doing empirical formulas, when you come up with a fraction in your formula like that, 3.5, then you just have to make it whole, right? So you make it whole via multiplying. So this is going to end up being what? Cl2O what? 7. That's a huge difference from ClO4.
Yes, sir.
Huge difference. So when you're doing the empirical formulas, it may be tempting to round that number up, but instead just make it whole by multiplying. So if it's a half, 3.5, 2.5, 4.5, you can just multiply by 2, and that'll make it into a whole number. So this is the empirical formula for a sample containing 5.31 grams of chlorine, 8.4 grams of oxygen. All right. So we're gonna, yeah, it's 150. We're gonna stop here. I want to give you, I gave the class this morning a little problem to work on over the weekend, but let me show you this diagram that I've been moving for the whole time. And we're going to, so this is basically the strategy for calculating empirical formula. So you want to take the mass of the atom, you want to take that mass and divide by molar mass. That's how you get moles, right? So you see here you got moles, and then divide by the lowest number of moles, and that'll give you your ratio. And then take that ratio, and if it's a if it's a fraction, you can convert it into a whole number, right? By multiplying through by some factor to make it a whole number. But this is, we're going to say if so we have a fractional number present, then we can do that part to get to the empirical formula. All right. So I want you to work on this over the weekend real quick. I'm just gonna give it as an on your own problem and then we're done. You have a sample. I'm just gonna abbreviate this. So you got a sample that contains 0.13 grams of nitrogen and 0.32 grams of oxygen. We'll discuss it on Monday. So work through it over the weekend. Should take you a few minutes. It's just like the previous problems. And we'll have somebody to present it on Monday. All right. And then we'll see what we got. All right. Any
Dr. Rush.
questions? Go ahead.
I was gonna ask, like, do we have to turn it in on that? What do we just gotta do it on our own?
No. You said, do you have to turn it in?
Yeah,
No, we're gonna discuss it on Monday. But I would like for somebody who does it over the weekend to lead the discussion. And and then at the end of that, we'll take, like, maybe we'll turn this into we'll incentivize it some kind of way. All right. Maybe not lunch for everybody, but something else.